Alright, let's talk about continuity and discontinuity, and a little bit about the intermediate value theorem. First thing, most questions in this will ask you where is this function continuous or where is this function discontinuous, or ask you things about the types of discontinuities. We don't have that many types, so it should be pretty easy to distinguish between removable and not removable, jump and step, infinite discontinuities, just holes, that sort of thing. Alright, first, the definition of continuity is pretty important. For every point on the interval, the limit needs to exist, and the value of the function needs to match that limit for every point on the interval. So that's what's set up here. This is what's in your book. This is like my words version of it. Basically, what it's saying is that we know continuous functions look like this. Like, so you don't leave your pencil off your paper, you don't double back and make it not a function. But even if these points are defined at the end, we can only guarantee continuity between the endpoints. We can't guarantee continuity at the endpoints because the limit doesn't exist for that point for this function, because we have nothing on the left side of this. So the limit as we approach on this side is there's nothing. The limit as we approach on this side is a defined value. We can't say, hey, it's approaching that side because it exists there, because the limit needs to be approaching from both sides. So, first thing is the limit exists for all points on the interval. This disallows things like jump discontinuities. If you have something like this, we'll make those line up a little better. At this point, the limit from the right side does not match the limit from the left side, and so it's no good. Infinite discontinuity, same idea. If we're going up to infinity on one side and going down from infinity on the other side, like a 1 over x sort of graph here, this is no good. The limit from this side is negative infinity, the limit from this side is positive infinity. And yeah, that's bad. Those don't match at all. Our second explanation here, that the value of the function matches the limit, is, hey, if your limit occurs, so like here on the graph, our limit occurs, does the value match that limit? And yeah, we're all good. So what this gets rid of is things like holes. Say if we had a hole on our graph that was all good here, and all of a sudden I warped a point up here, I mean, this is no good. The value doesn't match the limit at this point. And that's no good. Alright, so that's the definition. Next thing, removable discontinuities are holes. Non-removable discontinuities are the other two types, infinite or step or jump or whatever you want to call it. They're all the same, step and jump. Alright, the intermediate value theorem is important in this section just because we say it has to do with continuity. So if we have a graph and we have 2 points, you just pick any 2 points, you say that, hey, if I connect them, I have to go through all y values in between those 2 points if the function's continuous. And that's why it's brought up in this section. So this relies on continuity, the intermediate value theorem, but it's a really simple idea. All it says is, hey, if you're connecting these 2 points, you have to go through all the y's unless you break it and do something like a hole and warp up here. But that breaks continuity, so the whole idea of continuity making us go through all those points, that's what the intermediate value theorem is. Alright, very important for you to know in this section is the danger zones for continuity. The danger zones are holes, negatives in square roots, negatives or zeros in logarithms, and the intersections of graphs and piecewise functions. You need to check for all of these and see if it's all good or not when you're solving continuity problems. Holes look like this. So like a factor that cancels out on the top and bottom. Negatives and square roots. Yeah, I mean, that just looks like, this would be a problem. Negatives or zeros in logarithms. So say we had like natural log of x minus 4. This would be bad for x equals 4. It'd also be bad for anything less than x equals 4. So we'd say this is only continuous where x is greater than 4. And then the intersection of graphs and piecewise functions, you just need to test where they intersect. And by intersections, I mean if we have a piecewise function over here that's 0, 1, and 2, like as easy as possible, x is less than 0, x is between 0 and 1, so it's got to be there. And then from 1, where x is greater than this. Alright, this is a function that's defined for all values. Well, now it is. Defined for all values. However, if we're looking to see if this thing's continuous, it's not, because we're going from 0 to 1 and then from 1 to 2. So this thing would actually break continuity at x equals 0, so we could write our answer like this. It can't be equal to 0 because it breaks continuity there. And we could also say x is not equal to 1 because it breaks continuity there. And this would be an acceptable way of saying, writing our answer about the continuity of this function. Alright, there are a bunch more examples in here, but I'm going to mob this problem real quick. First thing, this is the problem we just did up here, like where we're testing values on the other side, but here we're trying to pick A and B such that this actually works. So I'm going to do that now. By picking A and B such that it works, I mean that I gotta plug in -1 on this side, and this thing needs to match 5. And then I gotta plug in 3 here, and so if I plug in 3 for x, I get 3a plus b, and it needs to be equal to -7. And 2 equations, 2 unknowns, just boom, subtract this guy, -4a plus 0 equals 12, divide by -4, and a is equal to -3. And then we just got to find b, so we can plug it into the first equation. It'll be easy. 3 plus b equals 5, b equals 2, and we did it. Oh, sorry, that was off the page, but yeah, it's just plugging it back in to the top equation. So this is an example of one kind of problem I can give. I can also give problems like this one up here, where you had to find places where it's not continuous. This is kind of a wide section with a lot of really important ideas in it. And that's it for the video.